Hey, this is Dr. B, and let's take a look at a bunch of questions about reaction rate. Let's begin by defining some terms. The rate of a reaction, also known as reaction kinetics, is really the speed, right? It's the time that's required for a measured amount of a substance to react. The reactants are the substances that are consumed. The products are the substances that are formed. The transition state is that transient state that's in between reactant and product. The activated complex is essentially the same thing. What's necessary for a chemical reaction to proceed? Well, they have to collide. They have to collide with enough force and at the right location. There are many ways you can change a reaction rate. The memory device STICC, hit it with a stick, is helpful. We can change the surface area, the temperature, the identity of the reactants. We can change the concentration. If possible, we can add a catalyst. Given an energy diagram such as this, where the y-axis is energy and the x-axis is the reaction progress, how much energy does the forward reaction or the reverse one need to proceed? Well, in either case, you need to get over the hump. So in the forward direction, it would be the energies that correspond to position 3 minus position 2. Or going in the reverse direction, 3 minus 4, and that would be a smaller activation energy in the reverse direction. The transition state occurs at the top of the hump. How exothermic or endothermic is the reaction? Well, you ignore the hump, since any energy that goes into it you get back, and you are only concerned with the beginning and final state. So energy numbers that correspond to 4 minus 2 for forward, or 2 minus 4 for reverse. How exothermic or endothermic is the reaction? Overall, you need those numbers, but it looks like it's endothermic going forward and exothermic going in the reverse direction. Here's some data, and given that, find the rate of the reaction. Well, first you need the change in concentration, which looks like it's 0.1 molar over time, which is 4 seconds. That gives us a rate of 0.025 molar per second, which, since we only had one significant figure for the time, we could round it to one significant figure. It's important to consider whether reaction rate and spontaneity, or that is thermodynamics, have some sort of inherent relationship. So, are fast reactions spontaneous? Perhaps, but not always. For example, iron oxidizes incredibly slow but spontaneously. If the free energy of a reaction is highly positive, so non-spontaneous, does that mean slow? Perhaps not, right? For example, if you electrolyze water into hydrogen and oxygen, it's definitely not spontaneous. You got to stick a battery on there, but it can go very rapidly given enough energy. Are fast or spontaneous reactions dangerous? Sure, sometimes, but always? I don't think so. Oh, baking soda and vinegar reacts very spontaneously, but most people wouldn't think of that as a dangerous reaction necessarily. And do they always give off energy if they're fast? You might think so, but imagine a cold pack. It very quickly absorbs heat from the surroundings and therefore is rapid but endothermic. Take-home message: there's no guaranteed relationship between rate and spontaneity. This is a look at several questions about reaction rate.